Welcome guys. So in this video, let's talking about Euclidean ring, Euclidean domain. Okay, so this is a hard topic. Yeah, basically I think maybe 30 minutes or something. And the next video we may talk about examples. But I just want to say that Euclidean rings, or usually people call it Euclidean rings, is a not easy subject. Okay, and there is still, I think, still open problem in it. Okay, so integral domain, let's give a definition. So integral domain R is called a Euclidean ring. If so for any non-zero element, so integral domain means commutative, and if A B is 0, you mean A 0 and B 0, or B 0. So given a non-zero element, there is a function called D, which define R to all the positive non-negative integer, such that satisfy the two properties. So first is that AB belongs to R. You must have dA less than dAB, or less or equal to dAB. And the second is that for any AB belongs to R, there is a division. So both non-zero. So both non-zero. Oh, by the way, these are also both non-zero. If you have non-zero, and you can always there is T and R, such that A is BT plus R. And then there are two cases. The first is R0. The second case is that dr less than dB. So if we satisfy both properties, the first is two non-zero element times it must be a dA less or equal to dAB. And then the second is that if you have any R, AB, belong R, you can find a T and R, such that A is BT plus R. And there are always two cases. The first case is R0 or dr less than dB. Okay, so this is just the division, right? Okay, so example. So first example is that integer, right? Integer is just integer is the Euclidean rings, and then you just take any element D to be the ring, right? So I think you just take the absolute value of R. Okay, and then you in the elementary school that you know that you can do the division, right? So for example, if let's take A to be 17, B to be 8, right? And you can write 17 equals to 2 times A plus 1, right? So D of 1, which is 1, is less than D of you need a D of B, right? So in this case, B is 8, right? So since you can do the division, and you can prove that however you can just force to choose that this less than this, right? So this is a quotient, and this is the remainder. Okay, so so this is the tautological example, a trivial example. Okay. Okay, so these type of rings is contains very special properties. Okay, so let me just give a notation. So let me just definition. So definition is if you have integral domain R called PID, so it's basically called principal ideal domain. Means that any ideal in R is the form of A. So basically, you can always find A such that ideal generated by A. So I already write this many times. This means that RA belongs to RA and R belongs to R. So this means that any ideal is generated by a single element. So any ideal is generated by a single element. So if we satisfy all this property, then this is called a principal ideal domain. Okay. Yeah. So yeah, and now we can prove the theorem. So theorem is that the Euclidean domain are PID. So Euclidean domain are principal ideal domain. Okay. Okay, so let's prove. Suppose you get some ideal belongs to the Euclidean domain, and if I is 0, then sure. If I is 0, then generate by 0. Okay. So second case that let's assume that I is non-zero. So there's a non-zero element. Okay, so I claim that there is an element A in I such that let's say this is A0. So there's A0 in I such that the D of A0 is the smallest. So it's the minimum. Okay, why there's always minimum? Because this is the all of DA, all of element plug in D will get a non-negative number, a non-negative integer, right? So the subset of non-negative integers always has a minimum. Okay, so I claim the ring just generated by this A0. Okay, so simple. Let's take A belongs to I, and we know that there is a T and R, right? So let's T and R such that let's do the division. So T is equal to A0 plus R. So I divide A by A0, right? And then by the Euclidean, we know that D of R. So there are two cases. The first case is R0. Oh, if R0, then if R0, right, then A belongs to A0, generated by A0, right? Because A is just TA0. The second case, if R is non-zero, that means D of R should less than, strictly less than. So D of AR is strictly less than DA0. So this is contradiction because I said DA0 is the smallest, right? So this cannot happen. This always happen. So this means any non-zero, any element in the ideal must be generated by a single element. Yeah, so proof is done. Okay, so we know that so now we know that the integer is a PID. Okay. Okay, so another theorem is that the Euclidean ring always has unit. Oh, sorry, I should say identity element. So some people like the some people use the unit element to talk about the identity in the ring, but I use identity because otherwise you will sorry, some people use unit to say that the identity of the ring, right? But I don't use this terminology because I feel it's confusing. Okay, so I use identity to denote the ring, the identity in the ring. Okay. Yeah. So the proof is stupid, right? Because if the proof stupid, right? Because I know that the ring is generated. The ring itself is basically ideal, right? So generate from some U naught or some U naught in ring. Okay, I claim that U naught is identity. The reason is that the U naught belongs to ring, right? So U naught must be U naught times C for some C. Okay. Now I take any element A belongs to R, then I get I know that A is X U naught because A is C inside here, so A must generated by U naught. So I can get AC equals to X U naught C equals to X U naught C X U naught because U naught is U naught. So A, right? So from here that we know that C is 1. Okay. So C should be viewed as an identity. Yeah. So I think I say U should be U naught should be identity. This is wrong. So C should be identity. Okay. Okay. So some terminology. If A is non-zero and B in R, and the people say that so just terminology. So now work in the general ring. A divides B. A divides B means that there exists a C in ring such that A is B is AC. Okay, so stupid terminology. A divides B means that B is the multiple of A, or B can be divided by A. Terminology. A divided by B means that B equals to AC. Okay, so lemma. Sorry, lemma is trivial. So okay, so somehow like I like to use A divides B. This is a notation. So it means that B is a multiple of A. So stupid lemma, A divides B, B divides C equals to must implies that A divides C. Okay. Second is A divides B and A divides C. Easy to prove that A divides B plus minus C. Third is A divides B, then A divides BX for any X belongs to ring. Okay, so proof is a trivial. So leave as exercise. Okay, so let's define a greatest common divisor. So greatest. So this is the elementary school, right? So but in the general ring theory. So usually people call GCD. So so what is GCD? GCD, let's say GCD AB is called D. So what is this D means? Okay, so satisfy this property. The first is that if D belongs D divides A and the D divides B. And also, so I should say D is the greatest, right? So which say that whenever you have C divides A and C divides B, then you must have C divides D. Okay, so this is the common sense of greatest common divisor definition. Okay. So some people use, so I usually write D equal to GCD AB. Okay. Okay, so given some lemma. So this is somehow a generalization in a number theory. So if you have a Euclidean ring, then you give me AB in R, and it's the this is GCD. Then there's a lambda and mu in R such that the D is lambda A plus mu B. Right, so this is the elementary school result. Basically, your greatest common divisor can be written as a linear combination of original A and B. Okay. So proof. How to do this? So define a set A to be RA plus SB, where R and S belongs to ring. So you take all the linear combination, and I claim. So this A, right? This A is a set. And A is ideal, right? So A is ideal. Check by yourself. So A is ideal. And now I know that Euclidean domain is a principal ideal domain, right? So there exist some elements. Let's say some element D belongs to A, right? Such that A is generated by D, generated B. Okay, so I claim such D can be greatest common divisor, or must be greatest common divisor. Okay, so I know that so I already say generate D, right? So by definition, D is a linear combination of A and B. The problem is that how can I show that this can be greatest common divisor? Okay, the reason is that let's see. Let's see. So let's see. So R has a unit, right? R is a unit, right? So I know that A is 1A plus 0B, and the B is 0A plus 1B. Those way, right? So now it tells you that what? It tells you that the D, right? So A belongs to A, B belongs to B. So D must divide A, and the D must divide B, because A is generated by D, right? So it means that A is any element in A must be dx for some x in ring. Okay, so it satisfies the first property of it satisfies this property. It satisfies this property. Okay, so we have this. So second is that we need to prove what? Second is that we need to prove what wherever you have this CACB, you must have C divides D. Okay, so let's check what's going on. Okay. Let's see. So if C divides A and C divides B, you must have C divides lambda A, right? And C divides mu B by definition, right? By our lemma 3, right? Our lemma 3 is this, right? So A divides B means that A divides any element times B. Okay, so now A divides A divides C, C divides. If we have C divides A and C divides B, then we'll have C divides lambda A, C divides mu B. So which tell you what? Which tell you that right, because lambda A plus mu B is D, right? So C divides D. So D is the greatest common divisor by definition, right? Okay, so this is the proof. So you just take this D, and then you know that these two, and then you get this. Okay, so definition. So if R is a commutative ring with unit element, or basically or identity element. So R is a commutative ring. Commutative ring. With unit element. And so A is called unit. It's called unit. So now okay. So don't confuse about unit and the identity. Okay. So R is A is called unit. Means that there's another ring, another element in the ring, such that AB is 1. Okay, so for example, the unit of Z means that you get something which times it, you become 1, right? So the unit is 1 and minus 1. For 1, you just times 1. So minus 1, you just times minus 1. So if there's a ring in a, if there is another element in the ring such that their product's 1, this is called unit. Okay. Okay, so lemma. So if R is an integral domain, and there's a unit element with unit element. Sorry, with bad notation. R is integral domain with identity, and suppose AB belongs to R, and A B belongs. So you have to suppose you have two elements such as A divides B and B divides A. Okay, then A is UB, where U is a unit. So this tells you that if you get A divides B, B divides A, that you must A must be equals to UB for U is a unit in R in a ring. Okay, so still be proof. So if A divides B, then B is XA by definition, right? And B divides A, B equals A is YB. Okay. So what? So B equals to XY B, right? Because YB is A, which tells you that XY B. Okay, so you can cancel B, right? Because this is the integral domain. So you get XY is 1. Okay, so Y is a unit. But Y is a unit. X is also a unit, right? By definition. Okay, so A is UB for some U, right? You can choose U to be Y. So choose U to be Y. Okay. Okay. Okay, so now still not lemma. R is a Euclidean ring. And then you get AB belongs to R. So if B is non-zero, you get non-zero. If you have non-zero and another unit and another unit, then D of A less than DAB. So remember that when I define a Euclidean ring, in general, I say that D of A less or equal to DAB, right? But then now it's strictly less than if B is not unit. So you times any non-zero element, non-unit will give you strictly greater. Okay, so you can see in the ring, right? If you times element which is not the same as plus or minus 1, then you get that you must increase. Okay, so the proof. So define A to be A is ideal. So I already write this 100 times. Okay, so I know that right, I know that D of A less or equal to DXA, right? For any X non-zero. This is definition. Let's see. Okay, so that means D of A is a minimum in A. For any D values, D of A is the minimum, right? So now let's say AB belongs to A, and if suppose that if DAB equals, so we now I want to show that if DA equals to DAB, then B must be unit, right? So if DAB equals to DA, I know that if DAB equals to DA, right? Then we prove a theorem. What we prove the theorem in that means that we prove the theorem before that if you have two, if your greatest common divisor can be written as a lambda a plus, can be linear combination. Okay, so yeah, let's see. So now we get DAB equals to DA, right? So now is we use the formal the previous proof that we know that if this is the case, right, then A must be also generated by AB. Okay. But if A is generated by AB and also generated by A, then AB must be AX or some X. Or basically one can write or another write in another direction means that A is the multiplication of AB. Okay, so you can take all the place. You can take an integral domain property, right? Because by definition, Euclidean domain must be integral, so Bx must be 1. Okay, so B is a unit. Okay. So what I'm trying to prove is that if you times any number which is non-union and non-zero, then you must increase. Okay, so now you know this is a very difficult subject. There are so many things we need to prove. Okay, so yeah, maybe I should separate into 3 videos. So the definition. So Euclidean ring. So if in a Euclidean ring, you can define a prime number. So that's called prime pi. So this pi is say to be a prime element if so whenever so this is the usual feature intuition, right? If pi is equals to AB, then what? By definition, if remember your number theory, right? If you have any prime which can product of AB, then A of B and 1 of AB must be unit. Okay, so this is common, right? In let's say in the ring Z, you write 3 times 1 minus 1 times minus 3. Yeah, so there are 2 ways to write it, right? But however, right, one of these must be unit. Okay, so this is called a prime element. Okay, so this is what should be our final theorem. If R is a Euclidean ring, and every element in R, so every element in R is either a unit, so it's either a unit or a finite product of primes. Okay, so recall that in the elementary school, right? You know that any given any integer, you can write them as the finite product of primes. If it's non-unit, right? So any element, every integer not the same as 1 or minus 1 can always be a finite product of primes. Okay, this is called a unique factorization domain. So for any ring which has this property, called a unique factorization domain. Okay, so what we prove is that the Euclidean domain is a subset of unique factorization domain. Okay. And we also prove that this is the same as PI. It's a subset of PID, principal ideal domain. So Euclidean domain is a much powerful, much restricted rings. Okay, so this is proof. Okay, so proof. Let's say induction on DA. Okay, so suppose that suppose in your word, right? So let's suppose in your word in your okay, so proof. So suppose in your word your DA are all 1, right? And then you can check. So this is an exercise for you to check that if your D is always the same as D of 1, then A must be unit. Okay, this is easy to check, right? Because we already proved that it's non-unit, then you times A. If A is non-unit, right? So if A is non-unit, then DA times 1 must greater than DA. But you say right, but this is nonsense. All right, so sorry, if DA is okay, so what I'm writing about. So what I'm writing is that I claim that if DA is a D of 1, then A is a unit. Okay. The reason is that if A is not unit, okay, so if A is not unit, then D of 1 must be less than D of A times 1, right? But I already said D of A is D of 1. So who tell you that the DA must be a unit? Okay, so the ground truth is okay. Okay, and for induction step, let's assume that all the elements, so let's assume that for all the rings such that, or all the elements such that D of X less than D of A is a product of primes. Okay, so then so this is the induction, right? So this is assumption. So my assumption is that all the element with D of X less than D of A is a product of primes. So then we hope to show for element which D of something is A, D of A work. So we need to show D of A works. Okay, so if A is prime, and we don't have to prove, right? We don't have to prove. Okay, the reason is that if A is prime, right? If A is prime, then by definition, right? If A is prime, then you can there's always one unit, right? So by definition, one of its must be unit, right? Yeah, this is definitely. But I mean, if A is prime, then you don't have to prove, right? Because what I will try to prove is that A is a product of primes, right? But A is already prime, so I don't have to prove. Okay. Okay, so we can assume that A is not prime. Okay, but this is trouble, right? If A is not prime, then A can there's a B and C, such that A can A can be written as B times C, and the B, C are not unit by definition, right? But we know that if you have non-unit, then D of B will less than D of BC, which is a D of A, and also D of C is less than D of BC equals D of A. So which tell you that the B and C can be written as the product of prime, right? Because by assumption, so B can be written as a product of prime. Let's say B up to something, and the C1 up to something. So then the A will be the product of this. Okay, so proof is done. So proof is stupid, right? So we first do the assumption. We first prove the ground. We prove the ground truth, and we suppose that any element which less than D of A is a product of prime. Then we work on D of A. Suppose A is a prime, then we don't have to prove. If it is not prime, then it must have BC. Right, but the smaller element can be written as product of primes, so the greater element finally becomes the product of primes. Let's see. Okay, so I think we can finish the rest. Yeah, it'll still be a very long video. Don't worry, I will post the time chat. Yeah, okay, maybe we separate the next video. Okay, see you guys next videos. Bye.